Hello everyone, today we're going to be working on example 4-9, and this example is saying that a distributed loading of P, which is pressure, of 800x PA acts over the top surface of the beam shown below. We have to determine the magnitude and location of that equivalent resultant force. So as you can see, it shows us this beam. It shows us its width of 0.2 meters, its length of 9 meters. It gives us that maximum pressure right here. It gives us the distributed loading. So the first thing that we want to do is, since it's asking us to determine the magnitude and location of that equivalent resultant force, what we need to do is, instead of working with pressure, we want to deal with weight. So that's the first thing that we're going to do. So weight is equal to the pressure times that width, where our weight will be in terms of newtons over meters. Our pressure should be in the terms of newtons over meters squared, and our width should be in meters. So we're simply going to plug in our information into that equation. So 800x Newton meters squared, and then we multiply that by our width, which is 0.2 meters. So that means that our weight is represented by 100, sorry, not 100, 160 x newtons over meters. So now that we have that, the next thing that we have to do is we have to determine that maximum weight on the right side of the triangle. So the next thing that we're going to do is we're going to redraw this, but now in terms of weight. So we're going to draw that right triangle. Right? And then we have that weight coming downwards because the pressure in the figure was also acting downwards. So we know that weight is going to be acting downwards. So remember, this has a length of 9 meters. And remember that right here, this is the maximum weight. So to find the maximum weight, we simply just have to apply the length right here to get that weight at this point of the triangle. So 160, so weight max. Let me rewrite that. Is equal to 160 Newton meters times 9 meters, because we know that the whole triangle has a total weight of 9 meters, and at that 9-meter mark is where we want to find that weight. And that should give you a total of 1,440. So now that we have that, we can now proceed to finding that resultant force, the equivalent resultant force, and the location of that resultant force. So to find a resultant force for a right triangle, you got to remember this equation. So F of R, or our resultant force, is equal to 1/2 of the base times the height, just like any other triangle. So here, our resultant force is equal to 1/2 the base. Since now we're dealing with this right triangle right here, is of 9 meters. And then our height is going to be that the value of the weight max. So 1/2 times 9 meters times 1,440 Newton meters. So that should give us that our resultant force is equal to 6,480 newtons acting downwards. So now we have to determine where this equivalent resultant force is because we found the magnitude. Now we just have to find that location of the resultant force. So if you guys remember, when it comes to a right triangle, let me draw this out real quick. When it comes to a right triangle, that resultant force lies somewhere about here, which is basically either, you could look at this two ways. Mm, it is either if you're looking from the left side, and if you want to find this place, the resultant force is always either, you could say 1/3 from the right to the left, or 2/3 in from the left to the right. So this is 2/3 of the length, and this is 1/3 of the length. So our resultant force is right here. So basically, you could solve for this either way, either multiplying it by 1/3 of the length or 2/3 of the length. You just have to specify it. So let me show that real quickly. So the location of our resultant force is equal to, if I were to choose the 2/3 length of the triangle, what I would write is 2/3 times 9 meters, right? So then I would end up getting that our location of that equivalent resultant force is 6 meters. But since I used this, I have to specify. So what I would put is 6 meters from the left side, right? Now, if I would have used the other equation, the 1/3 equation, it would be something like this. So if I would have decided to use the 1/3 equation, I would put that the location is 1/3 times the 9 meters. So I would put that the location is 3 meters from right side. So in a way, both of these are the correct answers for the location of that resultant force. It just depends how, if it's specified to find it from the like left side of the triangle, then you would use the 2/3 equation. But if you're finding it from the right side, you could use the 1/3. It's basically like when you're trying to determine the direction of a resultant force and how you could find it either counterclockwise or clockwise. Well, it's the same way here. In the end, that resultant force is always going to be in this place. It just depends which equation you want to use and just to specify either from the left or from the right side of that triangle. So with that, we can conclude this example. Remember, this example was asking us to determine the magnitude and the location of the equivalent resultant force. So the first thing we did is we took that distributed loading of pressure and turned that into weight. From there, we took that weight, that distributed loading of weight, and we found the weight maximum because we were going to need that for our equation of our resultant force, because in a way we needed that height, and that height in this example is represented by the weight max, and we multiply that by the length of the beam, and times that by 1/2 since it's a triangle. And from there, we determine the magnitude of that resultant force. And then from there, we use this equations to find the location of that resultant force. Thank you guys so much for watching this video. Please feel free to hit that thumbs up button. And if you guys would like to see more videos like these, please feel free to subscribe to our channel.